Welcome to Project 3 for ME416 Computer-Aided Design of Thermal Systems. This project involves finite element analysis of heat transfer in fins. The initial conditions that are stated in the problem, as well as the values we used in our initial assumption, are a base temperature of 150 degrees Celsius, temperature of the environment being at 20 degrees Celsius, a convective coefficient of 60 watts per meter squared Kelvin, and a fin width of 10 inch and a fin thickness of 0.1 inch.
For the first attempt, we tried a coarse mesh for quick results, and then tried a fine mesh for accuracy. For the final results, we used a combination of coarse and fine mesh, with coarse mesh at the base since there's negligible temperature change at the base, and a fine mesh of 1 mm element size on the fin part for more accurate results.
This graph depicts the temperature of the fin as we move away from the body along the fin. After a certain length, the temperature along the fin gets very close to T infinity, and it is no longer beneficial to have a longer fin. This is then determined as the recommended length for the fin. To calculate the ideal length of the fin analytically, we use the equations for an adiabatic and an infinite fin, while also making the assumption that the fin has uniform cross-section.
Here you could see the temperature distribution results in both 3D and 2D for a copper fin. Here are similar results but for the material aluminum. And finally, these results can be compared to the results from stainless steel fins. As is visibly noticeable, the length of copper is much larger compared to aluminum, with stainless steel being the shortest one. The phenomenon exists because the conduction coefficient of copper is much higher and it has a significant amount of heat transfer for a longer distance of x. We also increase the thickness of the fin to understand how the temperature distribution is affected by the thickness. The main difference noticed is the temperature at the end of the fin is much larger.
This table shows the results for 3 different types of material. The results from ANSYS matched the calculated results for an infinite length fin, but were still off by about 10 degrees from the ambient temperature, which was at 20 degrees. When we increase the length of the fin by 10 to 15 centimeters, the temperature at the end of the fin will reach the ambient temperature. Thank you for watching.